Okay, hello class. Welcome to lesson 3 of the course. We're going to be talking about domain and range today. So it's another way to describe a function and how to describe its inputs and outputs. And a lot like function notation, it's a little bit more efficient way to describe it than and mathematical way to describe it than in words. So as a warm-up, like we just introduced the definitions of domain. Domain would refer to all the possible inputs, and the range would be all the possible outputs. And so if you look at each of these, the question is like, what values could you input, and what values could you get out? And so if you look at these, x squared, what comes up there is like you're not going to get any negative numbers out. You're squaring everything, but anything else is actually okay. Like if you try to get any other number, it's really just the square root of that number. If you can square it, then you would get the number. And so all numbers can be plugged in, but all numbers greater than or equal to 0 would come out. And so that's how we talk about the domain and range in terms of like just language. And so we're going to talk about how to do that in symbols this class. The second one is actually a line, y equals mx plus b. So it's all numbers can go in and all numbers can come out. So the domain is all numbers and the range is all numbers. And for the third one, it's a square root. And so if you realize that you can, the smallest number that you can actually square root is 0. You can't square root negative. You realize that like you can't get any negatives out, but you're also restricted what you can put in. And so we can't actually put in numbers like 0 or 1 or -1 because those will end up with negative numbers, and we can't square root negative numbers. They just don't have any squares. And so all numbers greater than or equal to 2 will work for the domain, so the inputs. And the range is all numbers greater than or equal to 0 will actually come out. So you could get numbers, you could get like 0, but then you can get any number above that. And so it's just really squaring the number. Okay, so the learning goal is like we're gonna like look at the definitions of domain and range, describing domain and range. That's what we kind of just did a little bit, and then explain restrictions given a situation. And so part of domain and range, like part of the language that we have to write with symbols, is you kind of have to learn about the sets of numbers. And so this is kind of an interesting like history, but I'm just going to walk through this quickly. In the middle, there's the natural numbers. So they're like the counting numbers, 1, 2, 3, 4, 5, and on and on. They're really positive whole numbers, not in counting like positive whole numbers. Whole numbers are the naturals, but they're also 0. And so like it's just the idea that like you could have a whole, but you could also just not. And so like the invention of 0 happened. It's funny because it's like one of the numbers that my son had to learn, like what's 0? You have 0 minutes left till bedtime, that kind of thing. The next one is integers. We use Z. It's a German. Zahlen means number in German. Integers are all numbers between negative infinity and positive infinity. Like they go on forever, but they're just really they're whole numbers. Negatives and positives, and they're kind of used to that. We use a funny letter, and so we will stick to that letter just with mathematics. We use Z, but you might see this come up as I as well, but it's integers. The next one is rationals. So it's any number that can be written as a number divided by another. We'll recognize this as like a decimal number, but it's also like integers. So integers are all part of this, just like naturals are part of wholes, and wholes are part of integers. That's why we've got this kind of picture like this. But rationals are any numbers that have a repeating or terminating decimal. Irrational numbers are things that don't repeat or terminate. They're funny numbers. They can't be figured out by like dividing two other numbers. They're numbers like pi and square root of 2. And so they're separate than the rationals. That's why there's a different line. But together, all of these, pi, root 2, and the rationals, all the irrationals and the rationals make the real numbers. So this whole box here is all the real numbers. And it's basically all numbers, but we call it reals because there is something called imaginary. And this is an invented number system just so that like we didn't have to stop at the square root of negative. and we could keep going, and so we invented complex or imaginary numbers. Set notation is a way to describe the numbers, and so this is how we describe, instead of saying like, oh, all your inputs can be greater than or equal to 2, it's all real numbers. Instead we say, we write a little mathematical sentence, if you will. And it looks like this. There's a brace at the beginning. The first part, it tells you what number set you're dealing with, and so mostly we deal with integers or real numbers, but like there might be a case where we can be a little bit more efficient by using one of the other number sets we just saw. So we say like x is your variable. So for domain, we usually talk about x, and we call it as x an element of the real numbers. So that could be integers, it could be a different symbol, but this is saying x can be anything, except, so then there's the exception, x has to be between -3 and 5. This is a logical interval. It's written in the most efficient way. It's saying that x could be equal to -3, x could be equal to 5, that's what this line means, but x is bigger than -3, and at the same time x is less than 5. And this is a way to kind of just write that symbol, and we'll practice writing these during this lesson. So again, domain is all independent, all inputs, and range is all dependent, or the outputs. So looking at that -3 and 5, so the question is like, which one of these would make sense? And so I had this question before, and so I moved it here, and so it doesn't work as nicely after what we just talked about. But if you look at this, what makes the most sense is you have to really look at this idea of it opens up towards the bigger number. And so like if you look at this one here, x can't be smaller than -3 and at the same time bigger than 5. If that was true, we'd probably have to write two different like parts. We can also say it like this: x can be smaller than 5 and at the same time greater than -3, but the first one's actually more efficient. This is saying like x is literally between -3 and 5, and the graph would look something like it could be really anything, but as long as the x only exists between -3 and 5. State the domain range for this, and so we're looking at like what x can be, and we looked at a quadratic in the warm-up. X as an input can be really anything, and so we always set up the sentence looking like this. And so x can be all real numbers, so we can plug in positives, we can plug in pi, we can plug in √2, we can plug in any number. So we say x is an element of the reals. And then in the second part we write our restrictions, and if there aren't any restrictions, so if we assume that x can be anything, like as high and as low as it can go, there isn't a need for this section. So you'd actually just take this brace and end it here. And so the brace should end here. The range is all real numbers because it can be any real number. Like it doesn't say anything that it can't be decimals, so decimals can't exist. This is a quadratic. So we do say y can be any real number, but there is a restriction. Y can't be like less than -2. So we say y is greater than or equal to 2. Sorry, I said -2. Greater than or equal to 2. So it starts at 2 and then it goes above there. And if x was 0, then you'd have 2, and it goes up from there. And so this is saying y is greater than or equal to 2. Okay. Should have seen these operators before, but like it might be a little bit of practice and trial and checking your work to make sure that you're getting it correct. Okay, the next one's a straight line. And so we saw this in the warm-up, and we actually saw that x, really, if y equals x plus 4, x can be anything and y can be anything. So we don't really need the second section, and it is real numbers. If we ever had a dotted line, that would be the representation for integers, or you could just see the points. But since we have a solid line, it means we can have everything in between. Here's some points. So a dotted line could connect these, and then that would just show that it would go on forever. But because it's just the points, the function only exists at these 5 points. And so the domain in this case really is just -1, 0, 1, 2, 3. So we could just list it. We can also say x an element of the integers, because it's every integer, not every number between. But it's between -1 and 3. So -1 is the start and 3 is the end. And so that's what the domain would look like. All integers between -1 and 3, that's what the inputs are. The outputs are all numbers 0, 1, 2, 3, 4. That's actually all the whole numbers less than or equal to 4, because it includes 0. You could say all the integers between 0 and 4, but it's actually quicker to say just the whole numbers less than or equal to 4. And by writing W here, you're actually saying to stop at 0. You can't go below 0 anyway. If you don't like this, you can say integers, and you can put zeros less than or equal to y's less than or equal to 4, and that's totally fine. It's just not as efficient. You could also list the points, but it looks a little different. The range is y is an element of just those 0, 1, 2, 3, 4. You don't say what type of number they are because it's really just those 5 numbers, and so you just say y is an element of so you have that first part really, and you don't need the restriction. So y is an element of 0, 1, 2, 3, 4. Okay, so that's actually a new way of writing it, and it's helpful when you just have a list of numbers like this. Domain here, notice that 3 goes to 8, 4 goes to 12, 5 goes to 9. 6 doesn't go to anything, and so I was debating whether or not to take it out. But if 6 shows up there, it's just showing that like you can try to plug a number in, but if it doesn't go anywhere, it's not really part of the domain. And so like that's interesting to know because every x value has to have exactly one y value. And so if it has 0, like you might think, oh, it fails the function test. It just means it's not part of the domain. So the domain is just 3, 4, 5. That's it. The range is 8, 9, 12. And that's it. Okay, so some practice questions. The domain here is between 0 and 5, and it looks like it's every number 0, 1, 2, 3, 4, 5. So we can say the domain is the whole numbers less than or equal to 5. The range, you have to be like a little bit more careful. You've got to like kind of estimate what those points are. And it looks like they are whole numbers. You just list them because there's no real pattern there. So y is 1, 2, 4, 7, 11, 16. For the next one, similar, but it starts at 1 and goes to 6, so that's all the natural numbers. You could say the whole numbers between 1 and 6, you could say integers between 1 and 6, but if you say the naturals less than or equal to 6, that's the fastest way. And the range, you just again have to list them. So you go over and see what the outputs are, and you just list them. The next one, the domain, we'll assume that this goes on after. It's a line, so it's all real numbers. It's a solid line. It starts at -1 and goes up from there. And so it's all real numbers greater than or equal to -1. The range, it starts at 0 and goes up from there. So the range is all real numbers. The height is 0 and goes up. So it's greater than or equal to 0. The quadratic, we saw one earlier, x an element of the reals. It can be any real number in the quadratic. And the range starts at 3 and goes down. And so you write y is an element of the reals, and y is less than or equal to 3. In all of these cases, I've written y. It might be a good habit to write f of x. But if you write y, I think that's okay. The next one is a line, but it starts and stops. So it's all real numbers because it's a solid line. Starts at 0 and goes to 8. So it goes, x is between 0 and 8. And the range looks very similar. It's between -2 and 2. And this one's going to look almost identical to that. X is between -2 and 4. And the range is between -1 and looks like 15. And it's all real numbers because it's a solid line. The domain here is between -6 and -3. It's all integers between -6 and -3, or you could just list them. It's probably just as fast to list them here, but I just wanted to write it in a different way. X an element is the integers between -6 and -3. And the range, the best probably way is just to list them negative 11, negative 9, negative 7, negative 5, and I just put them in order. If you put them negative 5 to negative 11, that would be fine. The last one's interesting. It doesn't show up a whole bunch in this class, but it's nice to expose you to this. This is actually just integer inputs. So if there's a dotted line, you're only allowed to put in integers. And so the domain is all integers. The range is a little bit trickier. Because we're only allowed to put integers, that means that technically this point doesn't exist. And so it's not like they're all integers for y. And so I say all integers, but I just say that they're all odd integers. There is a better way to write this. You can say the range is like 2k plus 1, and so then where k is an element of the integers, but we'll leave that for advanced functions or for those that are interested to really play with that. So in this case, I think even going here is a little bit tricky, but we can't use every integer because 2 isn't possible because you can't plug in an x value to get to 2. So that's why it's just the odds. You can get to negative 1, you can get to 1, you can get to 3, but you can't get to like any other numbers. Okay, and there's practice.